So, why are we talking about hydroelectric power? Well, in 2017, it was America's leading renewable energy source. You can see in this graph a lot of detail, and it kind of breaks out the renewable energy there being 11%. Again, I'd like to point out this is in 2017. No updated graphs that I could find had this much detail in them. So, hydroelectric was 25% of the renewable energy portfolio, 6.1% of the total U.S. generation. It's present in 34 states. It is a clean energy and it is adjustable based on demand. And we'll discuss demand in greater detail later on in this presentation. So what is hydroelectric power? Well, the water behind a hydroelectric dam stores gravitational potential energy. As the water falls, this potential energy is converted to kinetic energy, turning turbines to generate electricity. In physics, potential energy is energy held by an object because of its potential relative to other objects, stress within itself, its electric charge, as well as several other factors. So hydroelectric power to electricity. The opportunities are it is efficient. It's 90% of the energy is converted to electric energy. It's renewable and abundant. It's storable and adjustable based on demand. It's cost effective, has a low operating cost, and it's also used for flood control. The challenges are it's extremely expensive upfront. There's a barrier to fish migration. There's a change to the ecosystem. It's a halt to natural distribution of sediment. It alters erosion patterns. And of all the energy sources, hydro has caused the greatest immediate loss of life because of failures. Here's the lineup, electric generation. You can see the efficiencies of hydroelectric. A large dam is towards 94, 95% efficient. That's pretty amazing. Small hydro, a little bit less. And then you got the lineup down here. Here are our locations. You can see there's some really dense areas for dams. This image is a little blurry due to the size of it. I apologize for that. But you can see out in northern Oregon, southern Washington State, you can see there's a really dense area. That's along the Columbia River and its tributaries. There's a tremendous amount of hydroelectric dams out there, and even in California, right down the center of California, there's a lot out there. And if you look down at Tennessee, northern Georgia, northern and mid-state Alabama, you're seeing the Tennessee River Valley there. There's a tremendous amount of energy basically flowing through that river. And that conglomerate there is capturing what it can. So a hydroelectric dam, there's two forms. There's pumped hydroelectric. We're not going to talk a whole lot about that, but I would like to explain it. And then there's conventional hydroelectric. That's what we're going to spend the most time on, is conventional hydroelectric. So a pumped hydroelectric is exactly what it says. It's a configuration of two reservoirs at different elevations that can generate electricity as water moves down through a turbine. Typically discharged during peak usage, which is 6 p.m. on typically Monday through Thursday. And then during low usage times, it's pumped back up. So if you picture a major city, it's using a tremendous amount of energy during the day. Let's say, it's 70 degrees today. It was a beautiful day, but let's say it's 85 degrees, high humidity, everybody's air conditioners are running. um, pretty hard. And business energy is being used a lot as well. That would be a good time to have a reservoir full of water at a high elevation. You can open up the gates and just bring that stored water through a turbine and generate the energy that you need to compensate for that city's energy usage. And as that flows down, maybe you get 6 hours, 10 hours, depending on how much energy you need. You let that run for 10 hours. And then later on that night, when the load is off our businesses, the load is off of our homes due to the high temperatures, you're able to turn on pumps and pump that water back up that elevation to the reservoir before. It's a great way to recycle energy and or water, and you also don't have to have a large feeder coming into that reservoir to maintain the levels. So that is how a lot of these cities, not a lot, very few do this, but that's how the cities that do this, that's how they control their demand. You've got elevated energy usage in these time frames, and they can offset that with this type of configuration. So conventional hydroelectric, that's the damming of a river. It's increasing and decreasing as demand fluctuates. So even then, I'll give you an example. Here in the state of Indiana, we have a hydroelectric dam. It's right next to, there's down the road from Belterra Casino and Hotel and Resort. It was a beautiful place in southern Indiana. And I'm sure that area peaks. I'm sure they're using that hydroelectric dam based on when that building itself is peaking. There's a tremendous amount of energy in that one site. So I'm sure they work together on controlling those peaks. Here's some generation basics. There's a lot of information on this screenshot. It's very detailed. This is the best graph I've found detailing the components of a hydroelectric dam. But some of the main things are the reservoir, the penstock, which is what the water flows through, the draft tube, the generator unit, the gate. The gate's what controls the amount of flow, and then the tail race. Turbine and generator. So this piece of equipment right here is really the key to many things, especially with hydro. A lot of the updates that some of these dams are getting these days are just these. So they're pulling out the old ones, putting new ones in. They're able to get more efficiency out of it, more power generation out of the same amount of water going into it. So water flows through the penstock during turning the blades. Blades turn the shaft. Shaft turns the rotor. Rotors turn and creates a magnetic field generating the electricity. The turbine here again, it's the key. It's none of this other stuff happens without the turbine. So turbines are used across power generation. You've got gas, coal, wind, steam, and hydro. So steam is oftentimes, if you have a coal plant, it is being combusted in a boiler, and that's creating steam. There's piping throughout that boiler. Turns the water that's being pumped through those pipes into steam, and that steam is pushed through a turbine. Same with some gasification plants or gas plants. And then you've got wind. Wind is completely different. Wind is being used as the catalyst to turn the blades. Sometimes steam is a big facility will have a process that requires steam. Paper mills are a big part of that. They take waste steam off of power plants, and they also, some sites, create that steam, and they're using, in part of the process, a turbine to help generate electricity on that site. And then hydro. Hydro is from the falling of water through that penstock. But all those technologies require a turbine of some sort. So what does the turbine do? Well, Michael Faraday discovered that moving a magnet inside a coil of wire would create electricity. The turbine and generator is the mechanism that converts the potential and kinetic energy of a moving fluid to mechanical energy. And this is an illustration of what that magnetic field looks like. So Indiana hydroelectric dams, there's 5 of them that I could find. There's not a whole lot of information on most of them. Markland Locks and Dams, I believe it's the biggest one in the state. You've got Norway Dam, Oakdale Dam, Twin Branch Dam, which is on the Wabash River, and the Elkhart Dam. So the Markland Locks and Dam is what's in this picture right here. So you can see it's very interesting. It's pretty big as well. And there's a total for all the dams in the state. We're looking at about 105.6 megawatts of energy being produced. So here's a better snapshot of the locks. So the Markland Locks and Dam was placed in operation in 1964. It's on the Ohio River. It's 1,390 feet, 95 feet long. It looked like there's 3 generators there. I could not find any information that showed me that that's what was actually there. So the 3 generators is what just by looking at a different picture, that's what it just led me to believe there's 3 generators there. It has a total generation of 81,000 kVA. So in Indiana, we're controlled by basically a third party. Looks at the generation of electricity and distribution. That party is called MISO. It's the Mid-Continent Independent System Operator. And it's true to what it says. It's about mid-continent. It goes way up into northern Canada. So it's an independent, not-for-profit organization that delivers safe, cost-effective electric power across 15 U.S. states and the Canadian province of Manitoba. MISO exists to provide an independent platform for efficient regional energy markets. Since 2001, we have fostered wholesale electric competition in the region, created greater system reliability, and established coordinated value-based regional planning. These are their words off of their website describing themselves. I will tell you, I've been to MISO. It is an incredible location. Very interesting. There's a whole host of information going in and out of that building. This is a screenshot from a couple weeks ago. This screenshot shows that the Indiana hub is at 51.05 megawatts of energy being controlled at that site. So you've got the Illinois hub. You just got all these hubs here that are looking at this. Now, this was created because you've got thousands of generation sites across the United States, and all that's dumping energy onto the grid. So what you get is you might have a generation site in western Indiana, but they might be selling energy to a city in Michigan. So Michigan might be buying the energy that's being produced here in Indiana, and there is no way to physically distribute the energy at this power plant in Indiana directly to Michigan. So Michigan is buying the amount of energy that's being put on the entire grid for their purposes. So it goes on the grid in Indiana, gets used wherever it gets used, but Michigan has bought it. They've bought that generation. MISO controls all this. They maintain this and they make sure that there are fair, unbiased practices being done throughout this entire region. Very interesting. So here's a fuel mix as of 9:25 a.m. this morning. So you can see on the right here, there's a total megawatts of 72,260. You see down below, there's 32,000 megawatts of coal, 22,000 megawatts of natural gas. Nuclear is 11,000 megawatts. Nuclear doesn't change very much. It's basically pumping. Every time I've looked at this, it's anywhere between 11,400 megawatts to up towards 12,000 megawatts of nuclear energy being put on the grid in this district. Wind, 3,900 megawatts. We got solar at 227 megawatts. And then hydro is going to fall in the other category right there, which right now at this time is 1,434 megawatts. Now, out of all these systems, hydro is one of the easiest to control. So wind, you either have enough wind to turn the turbines or you don't. And sometimes wind is stopped. They're not producing wind due to market factors. But take coal, for example. It takes several days to fire up a coal plant. And once it gets up and running, they don't bring it down. They don't shut it off just because you have a beautiful day like today when there's low load. There's not much air conditioning today. There's certainly no heating. There's just a lot of load that's not present on a day like today. So, but that coal plant's still producing what it's producing. They can adjust it, but they can't shut it off. So you have a baseline load with coal. Nuclear is a baseline load. Natural gas takes several hours to bring online and several hours to shut down, and it's very hard on the equipment. So they like to bring it on and let it run. These days, they were designed to come on quickly and control peak, but these days they're running them around the clock. So it's very efficient and it's very cost effective. But hydro, you just maybe not close the gates, but damper down the gates to reduce the flow, which reduces the output of the water or output of the electricity at that site. And what you get then is on the reservoir side of that, the water will build up and it'll rise. And maybe this week, since this week is going to be in the low 70s all week and in the 50s at night, maybe some of these sites are dampering down and collecting energy in the form of water in the reservoir up to its max levels. And the next week, if it gets really hot, they'll be releasing that water and really cranking out some energy during these peak demand times. That's how they're going to operate that. So I would expect hydro on a day like today to be very greatly reduced compared to normal situations. So this is a real-time loading. This is what's going on in real time on the MISO grid. In this, you can see the cleared demand, which is your green line, your light green line, medium term demand, which is your dark green line, and your actual load. So medium term is they're projecting what that's going to be. They have an idea what it's going to be in the next few hours. And then the actual load is they've captured that. It's in real time. It's logged. So here's the first hydroelectric power plant. It was built in 1882. It was located in Appleton, Wisconsin. So not very much information on this. I couldn't get a annual production on it, and I could not get a nameplate capacity on it. But I thought it was very interesting to see that it was all the way back in 1882. They were using hydro to produce electricity. That's one of the earliest pictures of this dam I could come up with. It's very interesting to look at this, and I believe it's called the Appleton Power Plant, and it's a historical site now. So, beneficial electrification. So, with all this energy we've talked about, hydroelectric being a big part of it, hydro has been a big part of the renewable energy market for years and years. All the way back into the 50s, it's been really producing a considerable amount of renewable energy. So, with all these other market contributions coming in, wind, natural gas, nuclear, the grid itself is reducing its CO2. So we can produce, as energy producers and providers, we can provide this electricity to our members or our customers at much lower emission rates. So you can see this decline. You can see some of the projected decline coming. So we've approached the point where there's less particulates being produced by the grid now than what there was 10 years ago. And it'll be the same in the next 10 years. So this is very interesting. This is great news as well. So some of this has to do with there's large solar farms that are being built. These wind farms, they started building those in the early 2000s, and they're still building them. So I would predict that what we're going to see coming forward is a lot of the turbines and hydro are going to be updated as that technology grows. The wind is going to be growing, and solar, we're going to start seeing it be more prevalent in our communities. So one of the national players, this one's close to home. It's very incredible. You've got the Tennessee Valley Authority, which, as we've seen on the map earlier, there's a huge conglomerate of dams on the Tennessee River and its tributaries. So it's called the Valley of the Dams. It's not just in Tennessee. Some of these dams I've driven by in the past. It's very incredible. And this covers just the Tennessee Valley Authority is in Kentucky, Tennessee, North Carolina, Georgia, Alabama, Mississippi, and Virginia. In 1933, the Tennessee Valley had 29 total hydroelectric dams. I'm sorry, it was established in 1933. There are 29 total hydroelectric dams. It provides power to 154 utilities and 5 industrial sites. It provides electricity directly to them. So you think of an industrial site down along the Tennessee River Valley area, Tennessee River and the Ohio River. These rivers have a lot of metal smelting plants and a lot of different things that use a tremendous amount of energy. And years ago, those dams would have provided energy directly to them, and that's just not changed. You got the Fontana Dam in North Carolina. It's the tallest dam east of the Mississippi. It was built in the 1940s. It's on the Little Tennessee River. It's 480 feet in height, 2,365 feet long. There's 10,230 acres of water surface, 3 generators at this site, and 293.6 megawatt generation. So you can see that dam is enormous. And if you think about what this does for the area, I know it's incredibly invasive when they build these to the Earth's surface, but once it's done, there's a tremendous amount of water there that can be used for multiple applications. Irrigation is one of the main benefits for the entire community around there, but recreation, there's a lot of tourism, a lot of money being spent in and around these areas because of that. So there's a wide range of benefits. Another national player is the Columbia River Basin. I myself and my family was out there in 2019. The Columbia River is a magnificent sight. It is absolutely enormous. When they say the mighty Columbia, they mean it. It is just incredible. What it's done to the landscaping around there. There's waterfalls all along this Columbia River Basin. The tourism is very great there, and some of the dams along that river are humongous. So we're going to look at some of those here. But the Columbia River that entire area is magnificent. So this was established in 1933 to 1942. There's 274 total hydroelectric dams. 40% of the U.S. hydroelectric output is on the Columbia River. 29 gigawatts, and it's in Canada. It's also in the United States, and it's along Washington, Oregon, and Idaho. This right here is a picture of Hell's Canyon Dam. Thought that was a very interesting dam. It's an old dam, and they just put it right there amongst the cliffs along the river.
Jeremy, we've had some crackles in the line. If you turn off your video, maybe the audio will come in a little bit clearer.
See if I can find that. Well, Dana, I don't know where that is. Can't get
That's
to
okay. No worries. Go ahead.
I apologize. So the Grand Coulee Dam is the largest output dam in the U.S. It was established between 1933 and 1942. It's on the Columbia River. It's 550 feet in height, 5,223 feet long, and I'm not sure what the acreage of surface is in there. It's when you look at it on the map, it is a very large reservoir. There's 18 generators on this site, and there's 6,809 megawatts of generation. Of course, everybody knows about the Hoover Dam. The Hoover Dam is the tallest in the United States. It was built between 1931 and 1936. It's in Black Canyon on the Colorado River. 726 feet in height, 1,244 feet long. There's 167,000 square miles of catchment. So that's how many square miles drains into this reservoir. There's 19 generators. That's a total of 2,080 megawatts of generation. Here are some pictures. This picture on the right is a picture that I took standing on that dam in 2018. The picture on the top left, my picture was blurry, but the person who took the picture on the top left of those turbines was standing in the same place I was when I took that picture. So very interesting. You can see the bridge there above it on the right and some of the buildings down below that are in that Colorado River on the downside of the dam. Some of the global contributors are, this one's in Canada. It's the WAC Bennett Dam. It was built in 1968. It's on the Peace River. Has a height of 610 feet, length of 6,785 feet, 10 turbines, 2,730 megawatt capacity. Here's the Sir Adam Beck Hydroelectric Dam. It was built in 1922. It was added onto in 1954. It's in the Niagara Falls area in Ontario. There's 26 generators and 1,997 megawatts of output. The Yangtze River Three Gorges Dam. This was completed in the last few years. It is the largest dam in the world. It is incredible, the size of it. So it's physically the world's largest dam. It's located in China. It was built in 2003. Its height is 595 feet, length 7,661, 34 turbines, 22,500 megawatts, 87 terawatt annual generation. And this dam, NASA had done a study. This dam has restricted so much water that it changed the rotation of the Earth. And NASA decided that the change was, excuse me, 0.06 microseconds. So that's kind of scary if you think about it. But that dam has changed the rotation of the Earth. So humongous. So what if the dam fails? Well, this is a picture in a news article of the Yangtze River Basin. This dam didn't fail, but they had to open everything up at 100% to keep it from failing. And that is even with the river downstream of this dam was already flooded, well past flood stage. They still had to open that up or risk failure of the dam. This was a June 29th Weather Channel video. It's the Yangtze River Basin had already seen major flooding even prior to the dam. A flood in 1990 killed over 1,500 people. And this dam was built for flood control and to produce energy for the district. However, they still could not prevent a recent flood here. It would have been in June of 2020. So it killed several people then, but nothing like 1,500. Here's another dam, Itaipu. It's in Brazil, Paraguay. It's on the Brazil-Paraguay border. It was built in 1971. It's on the Parana River. It's 643 feet tall, 25,000 feet long. So it's an incredibly large structure. There's 20 generators, and it produces 96 terawatt of energy annually. These are some of the global systems, some of the dams here on Earth. It is, the amount of water being restricted by these is incredible. And that's it. That concludes my presentation. So I hope you found it interesting. And any questions or anything like that, please submit them to Dana. Thank you.
So I'm currently looking at the chat in Zoom, monitoring to see if anyone has any questions to ask. While I give people a moment, I thought maybe you could talk not specifically about hydroelectric, but I want to say earlier this year, Duke Energy was covered in the news, investing into renewable energies and
Yes.
looking at their future in regards to coal. Could you talk a little bit about that?
Yeah, so I would say based on the natural production of stuff, you can see by a chart in here earlier, you can see that coal is typically around 40% of energy output. So a coal plant takes a tremendous amount of energy to even produce electricity. So they take that into account. So that coal plant is, you put 100 units of coal in, you get maybe 45 units of energy out. So whenever you look at a system like that, and you say, well, we've got to update that system and make it more efficient, and to do that update might be, $4 million or $10 million, which is really a very low number on industrial sites like that. But you can build a multi-megawatt solar array for much less money than what just that update does. And it does produce very well. And Indiana has a very good history of producing great output on its solar. So, and of course, wind in northern Indiana is a key location for the country for that. So I think it's just a natural, whether we mandate it or we make laws to penalize these companies for the low efficiency or the air particulates. I think regardless of that, I think the natural progression is to go with a renewable energy source, at least for now.
Wonderful. I'm still keeping an eye. I'm sorry?
So does that make sense?
Yeah, it does. Efficiency. That makes sense. Also getting the most bang for your buck. So efficiency is important. That does make complete sense. There was a comment or a question. What would it take for energy to be developed from a dam at Raccoon Lake?
Well, that's a great question. So Raccoon Lake just happens to be located on Park County REMC lines. And speaking for myself, that would be a dream come true if that would happen. I will tell you that dam is aged. It's healthy. It's in great shape, but it is an aged dam. And our power provider, Wabash Valley Power, is always looking for ways to invest in a renewable energy source in its own distribution areas. So I don't know if that'll ever happen, but when that dam gets updated, it's worth the conversation. Now, the fall, they like to see it'd be about a 30-meter fall in water. So from the 60 feet would be about a minimum on that. So whenever you look at the fall in water, it's got to fall through those turbines at a speed, and you can reach maximum velocity of an object between, I think you're looking at 29 meters of fall. So if there's not enough fall between the top of that reservoir to the turbine location, then they're not going to do it. Now, there are many different options. There are horizontal turbines now that were not very practical in the past. The water flowing through it with minimal fall has great output, and I just don't know. I think that when the time comes, Park County REMC and our power provider, Wabash Valley Power, combined with Raccoon Lake managers, are going to have a sit down and discuss all of our options with that. I think many of us here would love to see that.
So we're still taking any questions from our participants, but that is very interesting. I didn't know that there were horizontal options available. So thank you for sharing that. So
They don't have near the velocity, so the output is reduced. The install cost and the technology cost is much less than what it was years ago. So that's where it still has to be a long-term economical decision based on what power costs are versus install cost and production of that site are. And those are a lot closer together for those type of systems than what they were in the past.
all right. So thank you very much for presenting today, Jeremy. I will share this recording on YouTube and on the Vigo County Purdue Extension Facebook page. So if you're interested in viewing it again or sharing it with friends and family or coworkers, please do that. Thank you very much for joining us for this series. I plan on sending out a short post evaluation to see what we did well, what we can do better, and of course, what type of programming our audience would like to see in the future. So thank you very much for joining us, and hopefully I'll see you in the future.
Awesome. Thank you, Dana.
Thank you, Jeremy.